Great. Hello, everyone. Thanks a lot for joining us today. So today we have Dave presenting. Dave is a research fellow at University of Oxford. Before that, he was a postdoc with Chaba at University of Alberta working on sequential decision making. And before that, it was a PhD at the University of Cambridge, supervised by Zubin Garmani and Jose Miguel Hernandez Robato. His research focused on designing and analyzing simple and practical algorithms for decision making, with also strong theoretical guarantees. And today we'll talk us about Thompson sampling and in particular in which circumstances is optimal in the dimension dependence. Thanks a lot for accepting our invitation, and the stage is yours. Thanks a lot.
So yeah, hi everyone, I'm Dave. This is a bit of work I've done with Mark, whose surname you might recognize from sort of one of the earlier papers on Thompson sampling, and with Chiara from London. So Chiara, I think formerly Gergel student, if I'm not wrong.
Well, my postdoc.
Postdoc, my bad. Right, so yeah, we'll be talking about when and why randomized exploration works. So just a high-level rundown of contributions in case you're already an expert. Don't worry if this goes straight past you. So consider a stochastic linear bandit, d-dimensional. Sorry, give me half a second. I should have switched off the grid so that this is actually readable. Excellent. So yeah, consider a d-dimensional linear bandit. Suppose that we've got an action set that's a subset of a d-dimensional unit ball. And suppose that's nice. And nice here might mean, for example, an LP ball with no corners. So p not equal to 1 and not equal to infinity. Then this work essentially establishes that linear Thompson sampling gets a high probability regret bound, which is d root n log n, the same regret bound as we get for lin UCB. Although lin UCB attains this for any action set, not just sufficiently nice. And this essentially matches the lower bound, which tells us that no algorithm can do better than d root n in expectation. And this lower bound is for the L2 ball. So it satisfies our niceness assumptions. It does restrict us. So this is sort of the main insight. And the question as to why you might care is a good couple of years ago, someone's actually shown a counterexample, an action set that shows that linear Thompson sampling suffers linear regret for a specific action set. So it's not at all straightforward that linear Thompson sampling should work. And there has literally not been a previous regret bound for just unmodified, straightforward Thompson sampling, an algorithm that we essentially all think works. People in practice use it all the time. But we don't have a good idea of why. So the motivation. At a high level, let's just consider a simple setting, or really a generic setting. We've got some problem instance theta star in some set theta, and we have some action set. A learner sequentially selects actions in the action set, receiving after each one a real valued reward. It is random and depends on the action xt and depends in some way on theta star. Theta star might, for example, parameterize a set of reward distributions. And the aim here is that the learner wants to attain a high cumulative reward, so a high sum of these YTs. For some people, especially people based in the UK, a natural approach to this will be to say, well, okay, our model, I'll be Bayesian about this. I'll assume a prior over theta star, rather than treating it as a fixed unknown. I'll say it's random. And I'll pick a likelihood function which reflects how I believe that the random YT is generated given theta star and xt. And this gives me a posterior distribution at each step for theta star given the observations. Now, from here, the thing you might want to do is, well, you've got a closed form. You can manipulate this to a closed form expression for the posterior for the rewards y1 to say yn, and you could literally maximize the expectation. Except this is completely intractable. This is maximizing an integral over n many choices. And also, there's no reason you might think this is a good thing to do. So at the end of the day, theta star, it's a fixed theta star. It's not random. You've picked some prior, largely probably because it's nice to work with prior, it's computationally nice. So there's no reason to think that doing the exact thing under your choice of prior is going to be the best thing in practice. So instead, we might just want to do something simple. The simple thing to do, or a simple thing to do, is Thompson sampling. We have our posterior, we sample from this posterior, and we pick an action that is optimal if we were really facing the sampled problem. So we sample a problem instance indexed by theta tilde t, and we solve the planning problem as if theta tilde t was the true environment, the true problem, where x star of a parameter denotes the optimal action in that environment. Now, the appealing thing here is essentially that this is like divide and conquer. We have, say, the Bayesian community, which has spent some time figuring out how to model things in this Bayesian manner, how to construct probability distributions, and how to sample from them. So that's fairly well established. And we have our community, which has spent quite a bit of time figuring out how to do planning. And this essentially decomposes the problem of trying to get good regret, trying to maximize these rewards into two things, into sampling and into planning. And of course, yeah, these priors would be picked to make it computationally tractable.
So
Now,
I had a question regarding the previous approach that you suggested. I'm not sure I understood like what was the suggested proposal. Solve for action on the posterior. What does this concretely mean?
So we could just write down the expression from the probability of y1 probability y1 yn given x1 xn, integrating out theta star. And then we could maximize the expectation of the sum of these y's with respect to this as a function of the actions. Right, so we could call this P1 to n. Mm-hmm. This is over the y's, and we could compute the integral of the sum of y I equals 1 to n, d P1 to n as a function of the x's. And we could take a maximum over these x's.
Right. Well, I guess not really, right? I guess you would like pick like a measurable sequence of x's that map from histories to actions. Like
right.
The Bayesian optimal algorithm that can be computed by dynamic programming in belief space, no?
Yeah. So actually, for any it's you'd run dynamic programming on the entire n-step sequence of actions.
Right.
Doing it optimally with respect to these these distributions.
Right. Okay.
And yes, and you're optimizing over the x's have to be suitably measurable.
Right. Okay. So I agree that it's totally untractable. And
you don't want to do this, and that's one side of it. But also, I think the important thing is the prior is arbitrary. So at the end of the day, it's not even clear that you want to do this.
Right. Okay. Gotcha. That makes a lot of sense.
erase this. Okay, so yeah, it's solving it exactly all this sampling and planning. Since we have flexibility on what we're choosing as the prior, we could just try to choose a prior under which Thompson sampling does well. Now, question is, does this procedure make sense? And if you look at the literature on k-armed bandits, Thompson sampling k-armed bandits, the answer is resoundingly yes. In that, if we just pick, we have k-arms, we have a mean vector in 0, 1 to the k, we model the rewards as being Bernoulli's with mean given by the mu indexed at the selected action. There's a natural sort of Bayesian choice here. Well, there's a natural choice of a prior here, which is a uniform prior on the mean vector mu, sort of least informative choice. And then under that choice, the marginal distribution for sort of each entry is beta, which we know it's nice and tractable. This is all closed form. And the important thing is here, we've arbitrarily chosen this uniform distribution. It's intuitive, it's conjugate in that we get this beta distribution as the posterior. And it works. You get a Bayesian guarantee that is presumably, that must be optimal because the frequentist guarantee that you get for this is also optimal. So frequentist guarantee meaning that this works no matter the choice of mu, even if it's fixed, it's not random. And so it's robust. The choice of the prior, or under this choice of prior, we get robustness. And it's the intuitive prior to choose. So nothing really magical happened. We chose a prior, but it's only part of the algorithm. It works even if it's not true. However, if we move to the linear bandit setting, which in my mind is sort of the minimally structured setting beyond k-armed bandits, so as soon as you have some correlations, here we have an action set that's a subset of the unit ball, which is just arbitrary normalization. Our set of possible models or possible bandit instances is just RD. We pick a theta star in RD, and we generate the rewards the learner receives are just normally distributed with the mean given by the action chosen in RD in a product with this unknown theta star, say variance 1. Now, once again, there's a natural prior to pick here, Gaussian prior for theta star, just because it's conjugate, just because this leads to all the standard ridge regularized expressions that we know how to work with. It's going to be computationally nice. We have this usual design matrix that will come up repeatedly, and we have our ridge regularized least squares estimate. Keep that notation in mind. So here, for a Bayesian perspective, if theta star really is sampled from this distribution, this does perfectly. There are no problems. And I haven't read the Bayesian papers in too much depth, but if the model is true, I really can't, if we really are in the Bayesian setting, I don't see how this algorithm would break more generally. I think you could get guarantees in a wide range of settings for this. But in the frequentist case, if theta star is not distributed according to a normal, you could break this. You can get linear regret for this algorithm. I think on the next page I have I have the counterexample. So a couple years ago, Hamidi and Bayati constructed this counterexample. Essentially, they pick an arm set that's composed of 3 points. The origin, point A, which has a positive reward, and point B, which has a negative reward, with the trick being that A and B are correlated. So this is a sort of 3-point acute angle set in a high-dimensional space. Most of the directions are just empty space. And in particular, for most, if you picked a random direction, so for any direction here, here, and so on, the optimal action is 0. So what happens is, if on the first go, in the first turn, you pick B, you get a negative reward, and you update your model. Because A and B are positively correlated, you might conclude that both A and B might have on average slightly negative rewards. And once you do that, there is a good chance that the next sample will be in the other direction from A and B. And think of this as being in high dimensions. So actually, there are exponentially many directions in D that are away from the small acute corner formed by, small acute triangle formed by 0, A, and B. And each time you select action 0, you incur, well, some amount of regret. But importantly, the distribution you're sampling from does not get updated. If we have a look at the equations, our design matrix here gets updated with the outer product of zeros, so it stays the same. And again, our mean estimate doesn't get updated. So you have you end up with an exponentially small chance of randomly picking something again in this corridor, randomly ending up on A again. And each time nothing changes, so you're stuck, and you just repeatedly pick 0. Now, one thing to notice about this counterexample is it only works if the norm of the instance vector of theta star is roughly square root d. So that's fine, but that's something to keep in mind for later. And is there a solution? There's a standard sort of solution to modify Thompson sampling to inflate the posterior we're sampling from. So essentially to sample with the same mean, but inflate the variance of the sampling by a factor of d. And once you do that, your posterior expands and you gain some chance of sampling A. Yeah, there you go.
Yeah, so I think I understand the argument, except for what you mean by this positive correlation. Is this something that's encoded in the likelihood or the...
Well, it's linear, so what I mean is that this angle here is less than 90 degrees.
Okay.
So specifically, it's chosen so that the angle to theta star here, this is 90 degrees. So you have a positive correlation, small angle between theta star and A, large angle between theta star and B, and small angle between A and B.
Okay, right. Gotcha. Makes sense.
And if theta star is sufficiently large, you end up needing this inflation of factor of d, or some other trick to make Thompson sampling work. Thompson sampling by itself, with the likelihood you would like to choose, fails. There's a question of, hey, Chaba.
How is this using that theta star is big?
How is this using that theta star is big? You need, this only happens if the initial update is sufficiently big to make the probability of A and B small, or of A small.
Right.
So you need theta hat to change significantly upon observing B.
So big signal.
Big signal. Yeah, you really want on your first step to get the wrong signal, the signal that suggests that A is bad through the correlation with B. And you want the signal to be big so that you just never try A, or you have a tiny chance of trying A or B.
Got it. Yeah. And that happens at this boundary when theta star's norm is square root d. And the norm of A and B is, I suppose, 1 or something.
1, yeah.
Yeah, okay.
And the reason that theta star being roughly square root d is on one hand reasonable is because a sample from a Gaussian, from the Bayesian prior, would be roughly square root d. Their construction is actually with respect to the Bayesian regret, and they just show that out of the Bayesian prior with some probability, with constant probability this happens. So now the question is whether this is a natural thing from a perspective of, say, the linear bandit frequentist literature, where if you're scaling the dimension of your features up, I'm not convinced that there's a good reason to assume that the reward signal scales with it. So we have our arm set being, say, the unit ball, or at least normalized to be 1. We have a square root d norm vector theta star. So our per step regret grows as square root d. Now, 2 arguments for why it's fine. A, this is what happens out of the Bayesian prior and everything works fine in the Bayesian case. B, linear UCB doesn't care about the norm of theta star until theta star crosses the square root d threshold. So linear UCB regret is sort of the same all the way up until this threshold. If you have theta star greater than square root d, linear UCB ends up getting more. So that's a suggestion that maybe everything should be fine. But on the other hand, if you told me you've got a k-armed bandit where the average per arm reward or maximum per arm reward increases with k, that's, to me, a non-standard setting. And more so, suppose that you had a non-parametric setting like a Gaussian process bandit. What would it mean for the reward scale to increase with the dimension? It will be a weird scaling to impose. And I don't know if you can make the counterexample work without this theta star being square root d. So I don't actually know if this is really binding in the setting that I would think natural from the frequentist point of view. Maybe linear Thompson sampling works. Or I'll show you that it works as long as your arm set is nice enough.
I guess if your demand is that you want to be completely invariant to scaling rewards, and you have a fixed arm set, then you are running into this trouble. Because now you have to work with theta star of any magnitude, because that's how things are scaling. You have a fixed action set. So it's like, it depends on like what you think is reasonable. Like if you think it's reasonable that the algorithm doesn't need to know anything about scales of reward, and it should still work, it seems to be the counterexample that shows that in that setting, Thompson sampling is not going to cut it. But yeah. But if you're not scale invariant in this way, then okay, this example doesn't work. Yeah, I think it would be nice to have scale invariance if you can have it, and for if other algorithms have it, then it's like not having it is like okay, it's a bit of a problem. Maybe not a big problem, but a bit of a problem.
Agreed, but here's sort of the proof we're going to do is going to rule out this example by assumption of the arm set, and it's going to work for any scaling up to square root d, so that's fine. And the remaining question will be whether in this regime where the arm set is not assumed nice, but theta star is assumed to have norm bounded by 1, does Thompson sampling work there? Okay, you lose scale invariance, but do you really get linear regret, or is everything actually fine? Do you really need this big misleading signal? Or is it just that the analysis would be really hard to do unless we assume that it's the first step that messes things up? And for the first step alone to mess things up, you need this big signal. Because this counterexample, the calculation is very, very manual.
But it's also very intuitive, right?
It is, yeah.
By the way, like it's also weird that you use the sigma, or the counterexample is using that we have a lot of sigma to actually well, it's because the algorithm it is what it is. It's a counterexample against a specific algorithm, and so the algorithm is going to be hurt by a lot of signal, the misleading signal, because it's not interpreting it in the right way. That's what the example is kind of telling you.
Very different to standard agnostic lower bounds. Anyway, moving on so that we actually have time to talk about this paper. Okay, so zooming out a tiny bit, we've looked at this Thompson-Sapling procedure, which says, oh, you've got this prior, you've got this likelihood, you sample for a posterior. Really, there's a whole lot of algorithms in the frequentist world, so to speak, or at least in the bandit community, which says construct some simple distribution that you can sample from, either explicitly or implicitly, sample from it, and act optimally with respect to the sample. So, of course, Thompson-Sapling fits this, but also things like perturbed history exploration, where you perturb the rewards you've observed in the past, and then fit an estimate to these perturbed rewards. You have bootstrapping, where you might fit your estimates to subsets of the data. You have ensemble sampling, where you might run a bunch of models in parallel, which again are in some way perturbed, and choose these models in random. And all of these are in some sense similar to Thompson sampling. And for all of these methods, we don't have a fully satisfactory explanation of why they work. So the question I'm going to try to answer in the remaining 30 minutes is why and when do these randomized algorithms work? Okay, so recapping the linear setting, we have an arm set that's a subset of the unit ball. We have some fixed theta star, and we assume its norm is at most square root d. We have responses which have mean given by the inner product of the arm and theta star, plus some noise which is taken from an independent standard Gaussian sequence just for convenience. You can make it your conditionally sub-Gaussian or whatever you like. And the regret is sort of a pseudo-regret, the sum of the differences between the mean reward, the maximum mean reward, and the mean reward actually incurred. There's core tool in essentially all analysis of linear bandit algorithms, or at least all analysis since Janz's paper, is these confidence ellipsoids. So given the data, at each time step, we can construct a confidence ellipsoid such that theta star is in the intersection of all of these ellipsoids with high probability. So this allows for actions to be chosen sequentially, just the standard setting we have. And we're going to, so Janz's construction would look something like this. The ellipsoids are centered at the mean estimate, plus some multiplier beta t times the ellipsoid we have here. So this is the unit ball transformed by the inverse, square root inverse of the design matrix. And I've added a little gamma here and here, which will rescale the ellipsoid. This is going to be needed for the standard proof for Thompson sampling. Here, beta t is roughly square root d log t. And we set the confidence intervals, the confidence ellipsoids themselves, to be this object with gamma taken to be 1, so uninflated. So we have a theta t, confidence ellipsoid around it, and from now on, throughout this entire talk, we're going to assume that we're working on the event where theta star is indeed in the intersection of all of these ellipsoids. So the first answer for why Thompson sampling works, this is sort of the classical answer from Shepra, Goyo, and Abil Lazarik. It's via optimism. Optimism is a tool we know well from bandits. So to me, these proofs are essentially taking a hammer that we know well and modifying the Thompson sampling algorithm until it fits that hammer. But it gives insight, again, in how you get around this counterexample here, and it works for any ARM set. So optimism, in this case, the LinUCB algorithm of Yasin, works as follows. You pick an arm xt and a parameter theta t, for which the value is higher than the value of any other pair in the arm set product with the confidence set. So you choose the pair of arm and parameter that give the highest value out of those we think are plausible, out of the instances we could be in. This is a bilinear optimization. And we play the arm xt. The theta t is only defined here for later analysis. It will be helpful for us. We play xt, noting that this is, to the greedy, the optimal action with respect to theta t. And this gets us the standard d root n log n regret. So the alternative is that we might sample a parameter uniformly on the from the confidence set and play the action optimal with respect to that parameter. So question is, should this work? On the left, we have optimism, and we very carefully picked a specific parameter action pair that satisfies a condition that will let us make the proof go through. And the interesting question is, can you get away with just randomly picking a parameter and playing greedily with respect to this? Is there a reason to think that this should work? And from the computational perspective, the nice thing is this randomized method only requires linear optimization. And if we think about this, sampling uniformly on this set is essentially the same as sampling from a Gaussian distribution. These theta t's, these confidence sets, are essentially level sets of a Gaussian posterior. Bing-Shun?
Yeah, I have a question here for the for the left-hand side, the UCB part. It is Lee UCB, right? Not the super Lee UCB in that paper.
Yeah, just Lin UCB. Yeah.
UCB, right? Okay, thank you.
So on the right-hand side, we do know, and that's something that Mark showed in the earlier paper and Shipra before that, I believe, that if we inflate these confidence sets, if we sample from larger confidence sets with the inflation being a factor of d, then you can actually get a regret bound. It's not linear. The regret bound suffers an extra square root d, square root log n. It's possible the square root log n doesn't need to be there. I figure it depends on how you do the analysis. But this is the sort of standard inflated posterior proof. And this gets around the counterexample of Hamidi and Bayati by using this inflation. So to see how this works, I'll quickly run through the standard LinUCB regret analysis. We expand our regret by adding and subtracting the value of the optimal arm. The first term drops out due to optimism. We're left with a second term. The second term only depends on the difference between parameters, not actions. And that's then easy to control. We know the distance between these with respect to the design matrix. This is just how our confidence set is constructed. And we use that both theta t and theta star are in the confidence set. This is the very standard LinUCB proof. And we add with elliptical potential lemma to sum things up. So for this gamma inflated Thompson sampling, let's just introduce a shorthand. We'll call this value function or support function to be this j of theta, which is just the value you would get for a given parameter if you picked the best arm for it. So we can write the regret as j of theta star plus minus this j of theta tilde, this sampled parameter, which is now replacing the optimistic parameter. And we end up with this additive term, which looks exactly like before here, which we could just handle using the LinUCB proof. And question is what to do with this first term. Essentially, if we introduce theta minus, which is the minimizer of J of theta in the current confidence set, and we introduce little p, a lower bound on the probability that the value of theta tilde t exceeds the value of theta star. So this is a probability of optimism. Yes, Trevor?
Should it be condition in the past, or?
Yeah, condition of the past.
Okay, just a t index. Yeah.
Yes. So this is the conditional probability of optimism. Then essentially we can recover the same thing as before. We have our value of theta star minus the sampled value. The sampled value is definitely more than the minimal attainable value, J of theta minus, which is now not random conditioned on the past. And this J of theta star, well, on the event where we are optimistic, on the event that theta tilde t, the value of theta tilde t exceeds a value of theta star, this is upper bounded by J of theta t, and you end up paying a cost of 1 over p, this conditional probability of optimism. So this is the expectation of this event. And from here, again, this is of the form we're familiar with, of the same form as here. Essentially, these are just 2 points inside of the confidence set, with this being the value of this one being higher than the value of this one. We apply the same Cauchy-Schwarz trick. Now, essentially what we're doing here is we're throwing away in the analysis all steps but steps which end up being optimistic. We're paying a factor, a 1 over p factor, which is the average time between optimistic steps, multiplying this. And we're shoehorning everything into this optimism-based analysis. Now note that our regret increases with the width of the confidence sets, but also we pay a factor of 1 over this probability of optimism. So we have to make sure that even in the worst case, we have some probability of being optimistic. How do we ensure that we have some optimism? Well, in short, if this is the origin here, and we have our confidence set here, we know that theta star is somewhere in that confidence set. If we inflate our confidence set to be the set that we sample from, we can see that for any parameter in here, in the green area, its value is going to be higher than the value of any parameter inside of the inner ellipsoid. And we know theta star is in the inner ellipsoid. So if you do sample a parameter here, you are guaranteed to be optimistic. The trick is, if you inflate, if the sampling ellipsoid is large enough, specifically you inflate by a factor of, well, the ellipsoid by a factor of square root d, or equivalently the variance by a factor of d, then this spherical cup here, its volume is a constant proportion or lower bounded by a constant proportion of the volume of the entire bowl, and you get this constant probability of optimism. So your gamma ended up being d, so you pay an extra square root. Yeah, you pay this extra factor, you're paying a square root d here, and you're paying a constant here. And this gets you a regret bound that works for any arm set. At the same time, it's not really telling you anything about how or why randomized exploration works. Just telling you that if you sample from a sufficiently spread out distribution, you're going to get some samples that are optimistic. The optimistic samples work the same way that UCB does. You're shrinking the ellipsoid. It so happens that you're shrinking it in the most sensitive, greedily most sensitive direction. And things sort of work out. But at the same time, no one in practice, if you tell someone to, inflate, pick the model you think is true. Pick this Gaussian model, this likelihood is posterior, well, the prior is arbitrary, but the likelihood is the true likelihood. We do actually have Gaussian noise. And you tell them, okay, now inflate this by a factor of d. I think they'll be quite upset. This is generally you might, I don't know, fit your parameters on some past data, maybe inflate them a little bit to account for uncertainty, not inflate by the number of dimensions arbitrarily. And at the end of the day, this isn't how Thompson subligers run. This has nothing to do with carefully balancing exploration exploitation by injecting just the right amount of noise. This is injecting an overwhelming amount of noise and counting on a different mechanism getting your regret bound. Not to say this isn't a lovely proof. So an alternative answer to how randomized algorithm works is sort of given in our paper, in the paper I'm presenting now. And this is essentially going to revolve around actually analyzing the dynamics of exploration induced by the noise and by the geometry of the arm set. So the key ideas here, we're trying to balance exploration and exploitation. Now, exploitation is easy if the per step regret for a parameter theta is roughly the same as the per step regret for parameter theta plus delta, where delta is some small perturbation. So if small perturbations around a parameter do not change the per step regret much, that means exploitation is easy. You could be anywhere near the right answer and you're getting basically the optimal regret. So I've labeled this sort of condition as S for smoothness. And now exploration is easy if when you perturb the parameter by a little bit, by delta, the optimal arm changes by a lot. This means that small perturbations in the parameter space lead to large perturbations in the actions you take, and you're exploring a lot. And this I've labeled C for the curvature or strong convexity. So the idea is, if we have a setting where the regret doesn't change too much as you make local changes to the parameter, but the arm actually changes a bit as you do that, then you're both exploring a non-zero amount and you're only paying some controlled amount of regret for this exploration. You're balancing exploration and exploitation. And since this is a randomized algorithm, we should basically think over time in terms of the expectation or expected regret, expected exploration with respect to the distribution of the parameter, and not think too much about individual values of theta tilde t. Just what happens in expectation over the distribution of the parameter. So to make this a little bit more concrete, let's have a look at the actual geometry of the problem. So we have this function j, which I'm calling the value function of the support function of the action set. And one sort of key insight is that the optimal arm is given for a parameter theta, is given almost everywhere by, or for almost all thetas, this is given by the gradient of j evaluated at theta. The way to see this, if you've got an action set here, which is your graphic x, you've got the parameter theta that you're evaluating the gradient at. What's the arm you're going to pick? Well, slide a line perpendicularly to theta and find the point at the boundary of the arm set. This is the action you're going to play. This is the action with the highest inner product against your theta. And now, if you think about, so this is x star. Now, what direction would you move theta from here to make j increase the most? Well, you maximize the inner product with this vector. So to maximize the inner product with a given vector, you're going to want to move along that vector. And this essentially gives you that the gradient of j of theta is the same as the optimal action under theta. And so if we want to make sure that that the optimal action changes at least a little bit as you perturb the parameter theta. We might, for example, ask that the norm difference between two parameters is lower bounded by some constant times the norm difference between the parameters themselves. This is a strong convexity condition. So this is the condition we might ask for. On the other hand, we want the smoothness condition. What should this look like? Again, same definition, and remembering that the optimal action is given by the gradient. The per step regret, starting for definition, adding and subtracting our sampled value. And okay, this here stays the same. Here, we note that this expression, this j, is given just by j theta tilde t, comma theta tilde t. This is by definition the inner product of the optimal arm and the parameter itself. The regret is just the Bregman divergence, or a slight generalization of it if you don't have strong convexity and if you don't have pointwise differentiability. Oh, one quick thing. Why almost everywhere? This, of course, doesn't work if you have flat bits or corners, but so it breaks the corners. But for a convex body, you don't have too many corners, so you have countably many, so it doesn't matter. That's Rademacher's theorem. Right, so you have this Bregman divergence being the regret. And so if we don't want the regret to change too much as you perturb the parameter, we might ask for a literal smoothness condition, asking that the Bregman divergence is upper bounded by some constant m, and the norm squared between theta star and theta tilde. Could be any norm. Now, this is almost what we're going to ask for. We're actually going to ask that the Bregman divergence of j squared, not of j, is lower and upper bounded by the difference in some norm. This doesn't need to be the two norm. This can be any norm you like. But that you have smoothness and strong convexity with respect to some norm. Now, why j squared and not j? Notice that the gradient of j is essentially scale invariant. The arm you choose, the optimal direction, does not depend on how large the theta parameter is. So if you try to enforce this condition here, which is essentially equivalent to this condition without a square, so if you try to have that the difference between optimal arms is lower bounded by the difference in the parameters, this side is invariant to the scale of theta and theta prime. This side is not invariant. You can always scale these up on the right-hand side and break this condition. So you're not going to be able to establish an m that's independent of the norm of theta and theta prime for this condition without constraining in some way theta and theta prime. So we need to do something. And now note that if we look at the gradient of j squared, well, that's just twice j of theta times the gradient of j. J of theta itself is homogeneous. It just scales with theta. It's just an inner product. And so now this here, which is just the norm difference between the gradient of j squared at theta and theta prime, this is now approximately homogeneous in the sense that it scales the same with the norms of theta and theta prime as the right-hand side. So there is now hope that you can get this inequality to work. And likewise, you wouldn't be able to get the right-hand side of this to work without the square or without some adjustment, again, because these things scale differently without the square. But yeah, this is what we ask for our answer to satisfy. There's a final condition that the origin is inside of X. This is, I think, an artifact of the proof. We'll talk about it later. Okay, so with these conditions, how do we make things work? Let's assume that we're in what we're going to call the steady state regime. So we're essentially saying that we've explored a lot. The confidence set has shrunk a lot. I have a diagram a couple pages forward. I'll skip to it. Right, we're in a steady state regime. We have a small confidence set here. The arm set is here. Theta star is inside of here. And the norm of theta star is up to some constant factors the same as the norm of any parameter in the confidence set. So this is different than sort of a regime you might start in, where the norm of theta star might be very different to the norm of other parameters in the confidence set. So we're far along in the exploration. Everything has worked well so far. Now, if we have a look at the regret, and we're going to assume, for the sake, this is just a sketch proof, we're going to assume that the arm set is the unit ball, the L2 ball. This will make a lot of things maybe more intuitive, and we'll discuss what needs to change if we're not in the unit ball. So on the unit ball, we have a closed form expression for the optimal arm, that's just the projection of the parameter onto the unit ball. We know the Bregman divergence of J squared. That's just the norm difference squared. And here we also have that the second derivative of J is just identity divided by J of theta. So for our regret, just a second order Taylor expansion gives that it is the difference in norm between theta star and the support parameter with the Hessian here. And if you, this Hessian, we have the closed form expression. This just ends up being 1 over the value, the optimal value, J of theta star, times the difference in the norm. Now, this would have worked for for a wide variety of sets using smoothness instead of the closed form expression, this second order Taylor expansion with respect to the Hessian at some point between these two, on some point of the line adjoining it, is a standard result. We don't actually use it in the proof, but you could have gone that way. And what we end up with is, if we recognize this as the divergence of J squared, but the regret is roughly controlled by 1 divided by the optimal value times the Bregman divergence of J squared. And this you could derive for general arm sets. It's not just a coincidence that these two things are equal. And here we used that we're in the steady state to say that this is 1 over norm of theta star, rather than say 1 over norm of theta bar, which could be arbitrarily different. So smoothness lets us relate regret to this divergence squared. Right, so we have this expression. Because both of these are the confidence set, we can write their difference as twice the supremum of any vector scaled by this design matrix times the square of the confidence width. And we know the square of the confidence width is a d log n. So what we need to control is this supremum. This is essentially 1 over the smallest eigenvalue of the design matrix. So we need to make sure that all directions are adequately explored. And if only we can show that the design matrix grows as square root t divided by J of theta star, to cancel this J of theta star in all directions, then this expression will sum up to square root n, and we'll get exactly the advertised d root n log n regret. And so we're going to show this. This is where our curvature or strong convexity comes in. So again, we're going to do the special case for the L2 ball. Consider this is the expected increment in the design matrix given the sampling distribution of theta tilde t. And you could imagine having an alternative sort of sum of expected design increments matrix. This is this V bar T, as opposed to the VT matrix, which is the realized XT outer product. Then, sorry. Coming right back. Now, since we have a closed form expression for xt, this is just tilde theta t divided by the norm of tilde theta t. And since we've assumed that we're in the steady state where this norm is roughly norm of theta star, we can actually calculate this outer product. It's 1 over norm of theta star expectation of the outer product of these theta tilde t's. And this outer product, well, if we think of something from a Gaussian, this outer product, using that variance minimizes squared, this outer product is lower bounded by the variance of theta tilde t, which under the Gaussian sampling, roughly the same as sampling for this ellipsoid, is just Vt minus 1 inverse. So we get that the average amount of exploration, we're quantifying exploration as this expected outer product, is lower bounded by the inverse of the design matrix times 1 over j of theta star squared. And now, sure, this used the closed form expression for the unit ball, but really all we're doing is we're relating the expectation of the outer product of the gradient, which, okay, for the sake of seeing it in the standard, the way it's usually in the literature, the Poincare inequality gets you the expectation of the norm of the gradient of a function being lower bounded by the variance of that function up to some constant. So really what this is a Poincare inequality, a convex Poincare inequality, and we're using this curvature of strong convexity to ensure that this lower bound is not 0. This essentially ensures that we have some Poincare constant. Now, okay, so we have this sum of the expected explorations. We have that the per step is lower bounded by this expression. And we have what I'm going to call concentration, although it's not concentration, it's more of a two-sided tail inequality, which says that up to constant factors Vt and V bar t are the same thing. So essentially, Vt is the same thing as V bar t minus 1 plus the expected exploration. V bar t minus 1 is roughly Vt. And this expected exploration is roughly Vt inverse times 1 over norm of theta star squared. And if you multiply through by this Vt inverse, use that Vt upper bounds Vt minus 1, you end up that Vt squared is lower bounded by the square of Vt minus 1 plus identity times this 1 over j of theta star squared. And so the square of Vt grows in every direction linearly. So Vt itself grows in every direction as square root t divided by this j of theta star, which is exactly what we wanted. So we're getting our d root n log n regret. Now, okay, this was all assuming we're in the steady state where we can exchange the norm of theta star with the norm of any parameter in the confidence ellipsoid. What happens when we're not in the steady state regime? We're in the so-called transient regime. Well, here we have some theta star. We have a huge confidence set, confidence ellipsoid, and essentially the green area is all the area where you get an optimistic sample. At the beginning, because you're sampling from a posterior that's large compared to, say, the norm of theta star, you get optimism for free. And it just so happens that the threshold at which you stop getting this constant probability optimism for free coincides with where you enter the steady state regime. Now, in which you no longer need optimism. And in this transient regime, you probably also don't actually need optimism. It's just a nice, convenient tool to make the proof go through. In the transient regime, essentially, you could just rely on exploring in all directions sufficiently. But yeah, Luca?
Yes, I was wondering if you can give some intuition why theta star cannot be on the border of the confidence ellipsoid in the transient regime. Why it's true that you have this green space?
No, it could very much be on the border. Even if it's on the border and the ellipsoid is inside, so the width of the ellipsoid is smaller than normal theta star, you essentially end up entering the steady state regime. Or at least up to constant factors. So if the ellipsoid coincided exactly with the red bit, then up to a factor of, say, 1/4, you're in the regime where the norms are comparable. So if we think of this ball here, if both coincided here and you shrunk it by 1/4, you would have this ball here. And the key thing is that we're excluding 0 from the confidence ellipsoid.
Okay.
But really, we don't actually use this in the proof. This is you could think of a separation, but really what matters is that you have steps on which you have some probability of optimism and steps where you don't. The steps where you have some probability of optimism include the transient regime, and these steps you can basically forget about them. Optimism deals with them. So all we need to do is we need to bound the regret on the steps where you don't have optimism, and on the steps where you don't have optimism, you need to do the sort of proof that we've done so far. So like the split into transient regime and steady state's a nice starting point. Really the split is into steps with optimism, steps without, and it's just the steps without optimism that you need to handle. And the proof without optimism essentially ends up working like what we've shown so far. So yeah, this transient and steady state divide isn't actually needed. It's an optimistic versus not optimistic divide. And optimism, I don't think is needed. It just makes the proof easy. There's no reason not to use it for those time steps. Our proof requires that the origin is inside of the arm set. Essentially, this is built in because we started by proving it for the L2 ball. And the origin is inside the L2 ball. Then we extended it. And by the time we finished the proof, we sort of realized we've been using this property all along and couldn't quite see how to get rid of it. But I'm not entirely convinced there's any reason at all you should need this. Do we need the smoothness and strong convexity? Well, if we want this scale invariance up to square root d, it seems like we need some assumptions. But maybe if the normal theta star is bounded by constant, maybe things work without further assumptions. This proof works for the arm set being, for example, p between 1 and infinity. P1 is essentially the k-armed bandit setting almost, so one could probably sit down and do a custom proof for that. So linear Thompson something probably works on the L1 ball. The tricky question is, does it work on the L infinity? Does it work on the cube? And I don't know. On the cube, assuming that, does it work on the cube for theta star being up to square root d, which the counterexample doesn't really say anything about. The counterexample uses a very sparse set, a small acute triangle in a high-dimensional space. But what if you do cover all directions? What if you have this unit hypercube? Does Thompson sapling work? And the next question is, well, okay, if it doesn't work, maybe it still works if you restrain the norm of theta star to be up to 1. So really, I don't know whether the counterexample, which part of it is crucial, or whether both are crucial. The acute triangle and the norm of theta star. So that's something I would maybe like to get an answer for at some point in the future. Yeah, that's everything. Thanks, guys. Hey, yeah. Please speak up freely.
Yeah, like also have a question here. So for example, for each step, whether you can achieve optimism or not, is it related to the eigenvector of the covariance matrix of the past? I mean, basically you need to construct a covariance matrix, right? And it is on the past data. So whether the eigenvector, the direction of the eigenvectors impact, I mean, whether in, for example, current run T, you can achieve optimism or not.
Yeah, so if your matrix is shrunk, if your eigenvalues are very large of a design matrix, so the covariance is very shrunk, then the probability of optimism is going to be low.
Okay. Okay, sorry, is there any intuition for that? I mean,
sure. So it's if VT is small, the covariance is large, we're in this setting where we're sampling from this large set. And then the probability that we get something with higher norm than theta star, so something outside of this red ball, is large. On the other hand, if we've shrunk the confidence set we're here, in the worst case, if theta star is exactly on the boundary here, none of the parameters inside of the confidence set allow for optimism. Or better yet, if we go back to the inflated versus uninflated diagram here, if we don't have inflation and theta star is allowed to be anywhere inside of here, then you're going to place the worst case here, and then you get zero probability of optimism because there's no point other than this extremity in this inner set that attains a higher norm than this point. So if you're sampling from a distribution that has a larger support than where you believe that theta star is, or where it's likely to be, then you might get optimism. And again, this happens essentially automatically at the start of the algorithm because your sampling distribution is still very spread out.
okay, thank you.
Shaba?
Yeah, how is the curvature of the action set influencing the regret bound again?
It's the ratio of big M over little m. So it's literally the kappa.
So what happens with the alpha as SP goes to infinity with the
Both
curvature?
cases, regret goes to infinity.
Yeah. Okay. And so we don't know whether that's real or it's a proof.
It's definitely not. I'm sure it's not real as P goes
Not
to 1.
infinity. It doesn't go there. Yeah, actually, it will be mostly there, but yeah.
Right. So the upper bound becomes linear. Yeah. The upper bound explodes. But yeah, it explodes as it goes to P equal to 1. And P equal to 1 is almost the unstructured setting.
Yeah.
So that seems very artificial. Question is, the other direction as P goes to infinity, is that artificial as well? Or is that like a true effect?
Yeah. Okay.
Mark.
Yeah, just a comment on that. The funny thing with the P equal to 1, which is the multi-arm bandit setting, is that the proof for Thompson sampling for the multi-arm bandit setting has exactly the same flavor. We have this proof has the same flavor as the one for multi-arm bandits for Thompson sampling, in the sense that we really look at the, let's say, the evolution of the eigenvalues or the exploration and the learning that we do on any direction. And so, I mean, there is hope. For sure, we know that we can extend this kind of proof to P equal to 1. The idealistic way would be to unify them. And the difference between the multi-arm bandit proof and this proof is in the use of the strong convexity and strong smoothness. It's so the Bregman divergence that we use in multi-arm bandit is slightly different, and the way it's handled is slightly different, and it's not strong convexity and strong smoothness that is used, but some sort of, I mean, the proof is super calculatory, manual, let's say. So it's difficult to really figure out what's happening there. But I have the feeling that it's just a different notion of strong duality, strong convexity and strong smoothness that is used for multi-arm bandits, knowing that those two properties are like dual properties, and there is exactly the same thing happening in multi-arm bandits. So to me, at least for p = 1, it's mostly a matter of unifying the proofs rather than discovering something new. My 2 cents.
But the p = 1 proof very explicitly uses independence. So it's not that, even if we unified with that, it's not clear that this would give any insight for non-orthogonal arm sets.
Oh yeah.
Like, we could cover it as a special case of our proof, maybe, but it wouldn't, I don't think it will get us any further.
Just a quick question. Is the proof seems to be, I don't know, would this be extendable to like nonlinear version? Like, for instance,
GLMs should work, yeah, no problem. It should be just fine for the RL stuff. Yeah, I think you could extend this to all the usual suspects.
Right, thanks.
Chaba is unsure.
Well, with the RL, it's like people usually take the discrete action set case, but yeah, it's like LQR. Let's go with LQR or something.
Yeah, it's going to work for LQR.
It's going to work for LQR. Someone may or may not be writing that paper.
Oh.
Oh, also, is there a chance that you could prove that these strong convexity and the boundedness of the Bregman is a necessary condition? Like right now, this is a sufficient condition to obtain the correct, well, not correct, but kind of the desired regret bounds, right?
Yeah, and we have absolutely no idea, because the question is essentially, does p = infinity work or not? Actually, it's not necessary, because p = 1 works. And p = 1 has corners. Not a lot of corners, but it has corners. So this is definitely not necessary. At the same time, it seems like for this intuition of randomized exploration, injecting noise that balances exploration exploitation, it seems like you need some sort of properties which relate the parameters you sample to both the regret and to the arms you choose. So some notion of these two should probably appear. Chaba?
Yeah. But the dual question of that, okay, p = 1, maybe fine. P = infinity. As p goes to infinity, let's say you're in dimension 2 or something,
yeah,
and use finite time. Is the performance deteriorating to linear?
No. I mean, question is,
that's what the proof predicts, but
oh right. So if you take LP, yeah, I should actually try LP balls and see what happens as I increase P.
Yeah, you just like fix the horizon. And
what I've tried is I've tried simulating the cube, taking parameters that I thought might be worst case, and then changing the dimension and seeing how it scales with the dimension. And I never make it be anything other than something that looks like either D or D to the 1.5 without inflation. But question is, maybe I missed how to make a counterexample. I don't think so. I think because of how much symmetry you get on a cube, there really aren't that many ways to construct what a candidate for a bad parameter.
Yeah, like I wouldn't even worry about any bad parameter or anything. I would just choose a parameter, and then I would just change p and let p go to infinity. Right.
Yeah,
and see what happens with, I don't know, n = 100, right?
Yeah, that's probably the better experiment I should have run. I agree.
Yeah, that should basically decide, at least experimentally, of what's going on.
whether this proof. There's one more tiny thing to note. So this norm that the smoothness and shock convexity is defined with respect to. This can be any norm, and actually it doesn't even need to be a norm. It just needs to be some, not a metric. I don't know what's the minimum amount of properties it needs to have. And you scale with the best sort of norm or best two-argument function. So now question is, for these LP balls, to make the example, we explicitly pick a norm, compute the smoothness and the curvature with respect to that norm. By duality, you make some choice. And now the bound you get is because for our specific choice of this norm in the definition of S and C. Now, I have no idea whether we picked a good choice.
Yeah, I don't know how much wiggle room you have there. I would think that maybe you were clever to pick the right one, but yeah. So there is some qualitatively different thing about this hypercube with the corners, right? Because it's like the snapping to the corners is gonna happen, and of course with LP ball with P where it goes to infinity, it is something similar is happening, but the smaller the P is, because there is to 2, let's say, the less of this is happening, and you get some really smooth behavior, and that's a real effect. Whether that's going to influence the regret in a detrimental fashion, yeah, that's the question.
Here's
the effect is real. Like it's like the behavior is very different, because in one case it's like almost discrete-ish or discrete, and in the other case it's anything but that. Yeah. Okay, anyways, I don't have any insights.
The other aspect of it, if you think about zooming into one area of an LP ball, really you should be scaling with the local curvature and the local smoothness, not the global. And for the LP balls, the smoothness and the curvature were maximized at different locations over. So if you look at it locally at one part, locally it looks like an L2 ball. So if you zoom in enough, if you've got for long enough, you do eventually get to this L2 type behavior, I believe. So I believe asymptotically.
Yeah. So that kind of assumes that things get to the asymptotic regime, which for P equals infinity may or may not happen.
May or may not, yeah.
But for any finite P, yes, I agree.
So
you can refine the asymptotic expression to get rid of the dependence of the curvature. That should be the case. Like the local curvature is just like the L2 ball. Like, yeah, absolutely. So this is really much about this transient behavior.
Yeah.
Which is actually what the proof already shows. I mean, for any continuous arm set, basically, asymptotically, you will scale with d squared of t. The question is, how much time do you take? Does it take to get?
Yeah, that's right. Yeah. Good.
But I guess the question with changing this P and seeing what happens, I'm not sure I would have a good intuition for what's a reasonable increase in regret as we change P and what's not.
So, I mean, like if n equals 100 and you're in 2 dimensions and you're on a hypercube with whatever parameter vector, I don't expect linear regret. It's like, it should learn. So if the regret is going to the linear extreme, then like, yeah, okay, like I take that as evidence that this is not working.
I mean, it's not. I've run the cube many times and
it's not.
It works.
It actually works.
Yeah, like I've never practically managed to break linear Thompson sampling on the cube.
Okay. Yeah. Okay.
And now the only thing is...
Yeah. So my other question is, like, as a function of P, actually, is the behavior getting worse?
Right.
That's a more refined question.
Yeah.
And maybe the answer is no. And then like we know that, okay, like this proof is like just not capturing how things are in the finite time regime. And the fact that you say that like for the cube you didn't see anything weird happening maybe suggests that that's the case. And then wow, okay, like then what is the proof that would make this work and show the actual scaling? I don't know. It feels like, yeah, I don't know.
So there's one bit of funniness in that on the L2 ball, the worst case example, which you could achieve it with just any pick any theta star to be, say, constant norm, norm 1, any direction, it doesn't matter. You always incur at least a sort of root n regret, d root n. And this doesn't really depend on the choice of theta star. When you have the cube, you have an upper bound which says that you can achieve logarithmic regret as a function of theta star. So depending on the gaps. And so these two are in some sense not compatible. On the L2 ball and on all the LP balls, the asymptotic regret is square root n in the regime where the norm of theta star is constant. On the cube, if the norm of theta star is constant, the certain right asymptotic regret is logarithmic.
Sure. I'm like, that's clear. But that's a different aspect. I'm really focused.
It's a weird separation that.
Yeah. Discrete stuff is weird, and the cube is like discrete set. So.
But in some way, this suggests that as this LP, as this ratio of curvature goes to infinity, you should be. It seems that there should be some real effect because you're suddenly able, there's some transition into the regime where you are able to get logarithmic regret.
Okay, got it.
Yeah,
no, I don't think that it's suddenly like you can do that or you can never do that. I think that that's how it is. There's no sudden transition.
Well, by sudden I mean that at infinity, if you are on, you get log and regret, and for any finite p you don't. So it implies a sort of discontinuity in my mind in how these things behave.
That's true.
But only in a very asymptotic sense.
Yeah. Yeah.
All right. Amazing. So anybody else has some tricky questions?
Yeah.
I can stop the recording. Please
Something controversial.